Welcome back, Contemporary Math. We are in 10B. This section is about problem solving with geometry. So they start out, the first thing they talk about is the use of angles. And so we talked a little bit about angles last time. But if we have a circle, what we're essentially doing is we're dividing this entire circle up into 360 degrees. And so I'm going to use a little magnifying glass. So if I want to go right here, and I want to go, and I'm going to blow it up a little bit. This is just 1 degree. I can divide this single degree up into 60 little tick marks. And if I divide this little degree up into 60 little tick marks, 1 degree will be 60 minutes. And then I'm looking right here at one of these things. So if I look at 1 minute, and I divide 1 minute up into 60, you probably already know 1 minute divides into 60 seconds. Okay, and so we want to do a little bit of converting between measurements in degrees with decimals, and to convert between those in minutes and seconds. So they're going to start by giving us something with a degree in decimals, and they want us to transfer it into degrees, minutes, and seconds. And so the first thing, we want to start with the number of degrees it has. It has 4 whole degrees. And there are a few different ways to do this. But we have to account for that 0.63. So the first thing I would do is I would multiply 0.63 by 60. So that's the conversion factor. And so that's going to give me something like 37.8. So I have 4 degrees. I have 37. And I still have 0.8 I have to account for. So 0.8, I want to know how many seconds that is. So it would be 48 seconds. And I know I'm kind of glossing over probably like how these units are going, but this way we're multiplying by 60. This way we're going to be dividing by 60s. The unit, the conversion rate here is 1 to 60, right? And so we will do a section on units later, and I will go a little bit more into depth how this is done. But for now, I'm just kind of multiplying by 60 or dividing by 60 on this one, trying to make it a little bit shorter. So we have 45, and we have 45 degrees, 57 minutes, and 21 seconds. And I want to convert this thing into decimal form. So I know I have 45 degrees. This 57 is minutes. So if I want to convert 57 minutes into degrees, I have to divide it by 60. So these words are not words I say every day. Degrees, minutes, and seconds. It's like it's taking me a minute to go from degrees to minutes without saying hours somewhere in there. But yeah. So 45, 57 over 60. And then I have 21 seconds. 21, I'm going to divide it by 60. Put like another divide by 60. Well, I guess you can do that. This and divide by 60. We don't like fractions and fractions, and so like we're going to write it kind of shorthand. What we're doing is we're dividing it by 60 twice. We're actually dividing it by 60 times 60. Okay. And so work times 60 will be 36. And so now we're just plugging this into a calculator, figuring out what that decimal is. 45 plus 57 over 60 plus, what am I doing? 21 over 3600. I should be getting somewhere around 45.955833. I'm gonna say 45.95. It's probably pretty good. And I didn't tell you how many decimals to round to, so I guess round to enough is what I'm going to say. This one, it's not so obvious what you should round to. So if you're doing a problem, sometimes in context of the problem, you have to be accurate to what you're doing, right? Okay, so latitude versus longitude. Oh, I should throw the definitions in here then. Longitude is measuring what? Prime meridian. So these are also known meridian. Okay. So we have this sort of picture I stole from somewhere. Microsoft Illustration, apparently, somewhere. And we have a few questions on the next page that deal with this. So let's look at those questions, and maybe I can get everything on here at once. So Austin is approximately 30 degrees north and 98 degrees west. Suppose you could drill a hole straight through the center of Earth. So we're going to take our shovel, dig through the Earth, and what is the latitude and longitude you will arrive at? Okay. So I think right off the bat, if we're looking at 30 degrees north, I think that one is probably the sort of easier one to look at. So if I can do it. So if I'm up here at 30 degrees north, and I'm going to dig and make this line go through the center of Earth, you probably notice I'm going to end up at 30 degrees south. So the north-south, the latitudes, I don't use latitudes and longitudes every day either, so I got to remind myself which one is which. That one should be the easier one. If we're looking at the meridians, the longitudes, you might notice 30 degrees west is going to give me 150 east. And so I'm looking here, 30 and 150, I'm looking at 60 and 120 are opposites, 90 and 90, and then I go back to 120 and 60, 150 and 30. And so if we're looking at those, in each of those pairs, or I guess you could look at 0 and 180, you might notice those things add up to the same number. They add up to 180. And so what we're actually going to have to do to find the meridian or the longitude, we're going to have to swap so this one went from north to south. This one we're going to have to go from west to east, but we're going to have to do 180 minus this. So this and the other thing should add up to 180. So we're subtracting it from 180 to get our solution. And hopefully I did this right in my notes. That should give you 82. And we're talking about degrees east. Okay, and if you dig a hole straight through, will you end up in China? So that's the old fabled myth. But let's see where we do end up. So if I want to share my screen, let's share it. Let's do Google tab. And I want to do what? 30 south, 82 east. Look, I already looked it up in my computer. So if I go to my maps, you can actually look this up on Google Maps and see where it is. And it is definitely not near China. It is like in the middle of the Indian Ocean. Let's zoom out a bit more. A bit more. There we go. It's about direct midways between where? Madagascar and Perth, Western Australia. So this is known as antipodal. So this is called the antipodal point. If you know the word you could have Googled, you probably just could have Googled antipodal to Austin, and it would have gave you those things as well, right? And you could have avoided doing the dreaded math of doing 180 minus 98 because it's so difficult, but we're there. If you dig a hole. You're going to end up in the Indian Ocean. Suppose you travel 1 degree of latitude north or south. How far have you traveled? So this one, we're talking about latitude over here. So we're talking about traveling north or south 1 degree. The circumference of the Earth is 25,000 miles. So what we're doing is we're traveling 1 degree. If we travel 360 degrees, we will have traveled the full 25,000 miles. So essentially what we're doing for this latitude is we're dividing this amount of miles into 360 degrees. If we take 25,000 miles, and we're dividing that by 360 degrees, if you crunch those numbers, I'm probably pulling out a calculator, but you can get 69.4. And this many degrees for every 1 mile. No, I'm sorry. 69.4 miles, sorry, per degree. Set it backwards, sorry. So we're going to travel 69.4 miles for every 1 degree latitude that we go north or south. Okay. And so now we want to talk about longitude. So suppose we travel 1 degree longitude east or west. How far have you traveled? And so this one is a bit of a trickier question. And I want to look, can we see it? Like, how bold do I need to be with this is what I'm asking. So you might notice something about these. they are not the same size, right? And so longitude is going to really depend upon how far north or south you are. And so these things are, what do I say? These lines are not parallel. So these lines are parallel. We get the same distance here and here, right? So 15 degrees there is going to be 15 degrees there. We can go all along here. These lines are parallel. So we get this even sort of metric on the Earth, right? So this measures the Earth in an even sort of way. But when we do these lines are not parallel. So they are all intersecting. So it starts off really narrow up by the poles, and it gets wider as you get towards the equator. So it is widest at the equator. And so these things are not even. So what does it say? Note that they're not parallel. They are closer at poles, and the distance cannot be measured without giving a latitude. So you have to give a latitude. So they need to give you more info. So need the latitude. And then we could calculate it. It would be annoying, but we're not going to do that. But it would be possible. Okay. So that is the first topic we want to discuss here. The next thing is this thing called angular size and distance. And so if someone stands really far away, they're really small. If they stand really close to you, they look really big. And so we want to talk about this thing called angular size. And when we're talking about angular size, you might notice when they're really far away and small, this angle size is going to be smaller than this angle size when they're really close. And so that's what they're talking about by angular size. Okay. So we want to break this down, and we want to create a sort of ratio between two things that are similar. So we have two similar sort of shapes. So we're looking at this and pretend this is our little eyeballs over here on this little vertex over here. We're looking at this coin, and we want to look at the physical height of this object versus its angular size here. And so I'm comparing angular size and the physical object. So if I'm looking at this angle here is part of this whole circle. So I want to compare this angle size to the whole circle being 360 degrees. And I want to compare that. So this part is part of this whole. The same way the physical size of this object right here, if we go all the way around the circle, this is going to be compared to the circumference. And so we're comparing these two things. They should be similar. They should be the same ratio is what we're saying. This little angle part of the whole circle should be the same thing as the physical size of this object as compared to the circumference of this thing. So this is essentially, I think they might change around one thing in the book, but this is where they're getting this ratio from. We know that this circumference, instead of writing circumference, we know that the formula for circumference is what? Pi 2 pi r. And so if we look at what our radius of this circle is, this distance from your eyeball to the object. And so what I believe they have in the book is something like size of the object. Physical size as compared to 2 pi distance. So we have a few problems using this formula. And so this is what they're doing here. Oh, they rearrange a few things. Okay. That's what they do. So for angular sizes less than a few degrees, the following relates angular size, physical size, and distance. So this is kind of an approximate sort of thing. You might have noticed when I was going and looking back, I was looking at actually the base of this triangle versus like the circle here. So there was some like approximation going on there. So this is not an exact sort of formula, but it approximates things pretty well. And so that's why they make the stipulation you have to have angular sizes less than a few degrees for this thing to work. We're kind of squeezing things in where they don't go. The book does a little bit of rearranging. So if we take this previous formula and we solve for angular size, we're going to be multiplying by 360. So they solved this formula for angular size. We're just taking that previous formula. Angular size is going to be equal to physical size. And let me fix that pesky thing on my phone. Okay. And we're going to take physical size and multiply it by 360 over 2 pi distance. And so this is the formula that we're using, or that the book gives you. Okay, so the next thing, we have a few questions involving this. So they want to know, a quarter is about 1 inch in diameter. Approximately how big will it look if you hold it 2 yards, 72 inches from your eye? So we want to know how big it will look to you. So that is indicating that they want you to solve for angular size. We know the actual physical size of the object. We know the distance. So we're plugging in physical size and distance to this formula. And they're wanting to figure out angular. And so physical size is 1 inch. We're going to multiply that by 360 over 2 pi times the distance, which they tell me is 72. And this is one of those sort of calculator checks. Do you have technology? Do you have technology that you can use? You're probably going to want something to crunch some of the numbers in here. It will save you some time. It will save you some effort. I don't believe I can require certain things, but it will certainly be beneficial for you, and it will be worth money well spent. Okay. So if we do this, I'm getting 0.8 degrees. And that is rounding. So I got like 0.796178. Approximately 0.8. I'm getting over somewhere around 1 point. I guess it would be a little 796. Right. So this, I don't think, is probably the more interesting problem. I think the part B is a little more interesting. The angular diameter of the moon as seen from Earth is approximately 0.5 degrees. And the moon is approximately 380,000 kilometers from Earth. What is the real diameter of the moon? So we can use it sort of like this to find out the actual physical size of objects far away. And we want to look at this. We have this formula, angular size equals physical size times 360 over 2 pi distance. We know the angular diameter, that is the angular size that they're giving us, is 0.5. So we know this is 0.5. So do we know what physical size is? So we're looking along here. We know the moon, we know, is 380,000 kilometers from Earth. That would be my distance from Earth, from my eyeball here on Earth. But we don't know the real diameter. That's what they're asking. So the real diameter would indicate that we're talking about the physical size of the moon. And so we don't know the physical. But I know everything else. This is 360, this is 2 pi. And over on the right, multiplying this by 380,000. Okay, so there are a few ways you can solve this. You can do this in one swoop if you know what you're doing a little bit. This is multiplying. If you wanted to reciprocate this thing, multiply it to the other side. That's one way you can go about it. I'll just break it apart into a few more steps. I think it might help some people. So 0.5 equals physical size. I'm going to get lazy and probably just write physical size or physical. 360, and I divide it by 2 pi times 380, 1, 2, 3. And for pi, if you use 3.14 for pi in this class, I think you'll be good for pretty much everything. 3.14 is a good enough approximation. I use that sometimes. Sometimes I actually use the little key on my calculator, which is more accurate. That's not a pretty number. So what I would suggest doing is doing the reciprocal for this thing. I think would be the easiest thing. This gives you a really small number, and I think best thing, if we want to make this 1, we're multiplying by something, so we have to divide by this. Dividing by a fraction is the same thing as multiplying by the reciprocal. I think that's the easiest way to go about this at this point. And again, we will do more sections with unit analysis and things of that nature, where we will go more into depth with this. And so we want to do this. So we want to do 2 pi. We want to multiply that by 380,000. We want to divide that by 360 and multiply it by 0.5. And I should get 3316. And I'm talking about kilometers. The moon is 3,316, approximately that many kilometers in diameter. Okay. The next thing we want to talk about is pitch, grade, and slope. So I think before I even say anything, if I asked you what slope is, half the people would tell me rise over run. That's a fair definition. So I want to give an example to kind of differentiate these three things. And so if I do rise over run, and maybe you have like a line and you have 2 points, and your rise is 6, and I didn't draw this to scale, definitely. But if we had something that looked like this, you would probably tell me my slope is 6 over 16. And I would tell you that's minus half points because you didn't simplify that fraction. And I'm really picky. But anyway, divide everything by 2, and you get 3/8. So if you tell me 6/16 or 3/8 would be probably the more appropriate thing to say. When I'm talking about slope, we typically try to give you the reduced fraction. So I would say the slope of this thing is 3/8. If I'm talking about grade, if I'm talking about your grade, I'm going to give your grade as a percentage. So we want this thing as a percentage. So if we look at 3/8, I'm going to go probably throw this in a calculator to figure out what the heck that is. You could do your division by hand if you want, but I'm going to throw that out there. So that's 0.375 if I put it into decimal notation. If I want this as a percent, I have to move the decimal 2 places. So this is 37.5%. So that's how I would describe this thing as a grade. And so maybe you're asking, but where do we use grades? So grades are pretty commonly used when we talk about like road construction and things of that nature, I think. Pitch would be like if you're talking about the pitch of a roof, right? Okay, so there are 2 sorts of ways we could talk about the pitch. 16 or 3 and 8. So these things are essentially all the same thing. It's just the way that we talk about them or the way that they're phrased, right? Okay. Suppose a road has 100 grade. Okay. So if it has 100% grade, the first thing I probably want to do is think about what 100% is as a decimal. So is 100 over 100? This is one way you think about it. Or it's like 1.00, right? So they want to know what the slope of this thing is. So I guess we could do the 100 over 100. So I would not do that for my slope. So if they asked me the slope of this and I was in my other math class, what I would tell them is I have a slope of 1. Typically, if it's like 1 over 1, if you just have a number over 1, you just put the whole number there. So this would be a slope of 1. Or am I even saying commonly we use m to talk about slope. So that's my slope. What is my pitch? And I kind of talked about this. If this is 1, I can always write 1 as being 1 over 1. And so my pitch is going to be 1 and 1. And then we asked kind of a weird thing. What angle does it make with the horizontal? So if you have a slope of 1, I guess we could draw our axis. If you want to draw your axis, is that line running 1, right down the diagonal? And so if we're thinking about this, this is 90 degrees. This is diagonal directly down the middle. That would be the 45-degree line is what this thing is. Okay, so now I think this question is probably a little more interesting. Which is steeper, a road grade with 15% grade or a road with a pitch of 1 and 8? So there are a few ways you can do this. If you have a 15% grade, we want to put this into decimal. So that would be 0.15. If you have 1 and 8 pitch, you can put that as a fraction. If we want to convert this to a decimal, 1 and 8, by hand, or you can throw it in your calculator, but it's going to give you 0.125. If we're comparing these two things, I'm looking at 0.15 versus 0.12. So this 5 is larger. So I can say that this is larger. Another way you could do it is knowing this is what, 15 over 100. You could look at these two fractions and you could do that sort of butterfly thing if you do it correctly, right? 100 times 1 will give this 100. 8 times this will give this 120, I believe. What's that, 40? Yeah. So 120 would be larger than the 100. We're talking about going across here. Okay. But definitely the 15% is larger, or it is steeper. So what is steeper, a roof with a pitch of 2 and 18 or a roof with a pitch in 3 and 21? So 2 and 18, and if you simplify things, it might make your life a little easier. This is 2 and 18 is 1 and 9. 3 and 21 is 1 and 7. Woo! And now the textbook question of the day. Which one of these is larger, 1/7 or 1/9? I know the 9 is larger, but it is a fraction. Don't fall for it. 1/9 is smaller than 1/7. So this one would be steeper. 3 and 21. So I know there was an A&W burger. So most burgers are a quarter pound. They sold a 1/3 pound burger for less money than the quarter pound burger, and I think Americans are probably just not too good at their fractions. I don't know what to do with, but it did not sell as well. It was more food for less money and didn't sell as well. So not sure, but it did happen. So for a right triangle, we want to talk about Pythagorean theory. So I think most people can tell me and like mumble it in their sleep. A squared plus b squared equals c squared. I don't even know if they know what it means most of the time, but there it is. For a right triangle with side lengths a, b, and c, where c is the hypotenuse. So this is the thing that is really important, that we have a right triangle. The hypotenuse is the long side that is opposite to the right triangle. Then we have two other legs, and we can kind of label them however we want. One of them's A, one of them's B. It doesn't really matter which one you label which, right? And so this came from the Pythagoreans. The Pythagoreans were a sort of number-obsessed cult that existed. Pythagoras was one of them, but he really started kind of like a cult sort of following, and they worshiped numbers, and some of it was valid math, some of it was a bunch of numerology that was kind of silly, but they had their own kind of sect and beliefs. It's kind of interesting if you read up on them. Next page. So we know this Pythagorean theorem. If we have a right triangle, we can find the hypotenuse. Now we want to look at this problem. You travel 5 blocks east and 7 blocks north from your house to school. Each block is 1/8 of a mile. So down here, I guess, is my house. Up here is the school. And each one of these blocks is going to be 1/8. And so there's a few ways you can write this down. You can write down 1/8 plus 1/8 plus 1/8. You could do that. And then you can keep adding 1/8 plus 1/8 plus 1/8. You could add that. Just like that. Or you might notice you have 1/8 and you're adding it, what, 5 times? So I'm doing 5 times 1/8, and then I'm doing, what, 7 times an 8? Well, I'm doing 5/8 plus 7/8. Should give me 12/8. I'm dividing both by, what, 4 halves, I believe. So I'm doing, what, 1.5 miles and 3/2 of a mile. And that is to get to school. So that is 1.5 miles going around the outside of this. So the book, I have to put my 1/8 through 3 miles in here. The book, saying as the crow flies, and what they mean is they make a straight path from one object to the other, like you can fly over buildings, right? And so how far is it from your house to the school? From a straight line from one to the other? And so if we're looking at this, I'm going to redraw this picture. And so I know this bottom, I'm going 1/8 5 times. This bottom should be what? 5/8. This side then should be 7/8. And so we don't know what this thing is, but you might notice it's opposite of my right angle. So I'm probably going to let that be my variable C. I probably don't even really need to use the variable too much. I could probably just avoid algebra for the most part. But I know A squared plus B squared equals C squared. And that relates to a right triangle. When I square the legs and add them up, it should be equal to the hypotenuse squared. And so if I'm looking at this picture and I'm looking at this equation, hopefully you're piecing these two things together and saying, hey, I can use the Pythagorean theorem to figure out this value over here. So 5/8 squared, 5/8 squared, would be my C squared. And this you want to be kind of careful on. If you have to write it out twice, you can write it out twice. But this is 5/8 times 5/8. And we'll probably write it out twice. We know how the definition of a square is. Same thing, multiplying itself. And I'm going to throw my C squared over on the left side. So I'm going to move that over to the left. But this is 25/64, so I talked briefly about multiplying fractions. But we multiply straight through top, we multiply straight through bottom. We do the same thing over here. This is 49/64. So my C squared is 74/64. And the last thing, this is going to be my C squared. So I still need to do something, and hopefully you have some sort of calculator to calculate this, because this is not going to be a pretty number. I need to take the square root of this thing, whatever the heck it is. So if I take the square root of 74/64, I should be getting somewhere around 1.075, and that's approximating. It is giving me this big long decimal here. And so what I'm talking about is that line there is about 1.075 miles. And so we maybe want to step back and when we answer a sort of real world problem and make sure like our answer makes sense in context to what we're talking about. So we were talking about this thing, and if we walk around the outside, it's going to be 1.5 miles. If we walk a straight line, it's going to be 1.075 miles. Does that make sense? Should it be less than walking around the outside? Yeah, it is, absolutely should. You're walking a straight line, it should be the shortest path. And we know what? This is 5/8. We know that this is 7/8. We know that this should be more, a little bit more than both of these, right? Which those are a little bit less than 1. 7/8 is a little bit less than 1. That's a little over 1. It's about where you would expect it, probably. All right. So I think it makes a little bit of sense into the context of the larger picture, right? So always stepping back and thinking about these things definitely helps. Okay, so we have another example. We want to find the area of the given land plot in acres. So maybe ignore that the one in acres at first. So let's find this land plot. We want to find the area of this thing in square feet. Let's go for square feet first, and then we can convert it to acres. So if I'm looking at this, I say this is my right angle, and so this must be my hypotenuse. So I don't know what this is, so this might be the thing to let my variable be. And so I know this thing is either an A or a B, so it's one of my legs. So you can kind of pick whichever one you want it to be. But I know A squared plus B squared equals C squared. And so I know A squared, and now I guess you have to be a little bit careful. My B has to be the 300, right? If you pick the other number, you're picking your hypotenuse, which has to be your C. So my B has to be the 300, my C has to be this 1500. And I'm plugging these things in and squaring them. So A squared is going to give me 9 with 4 zeros. Going to give me 225 with 1, 2, 3, 4 zeros. And so if I subtract these two things, so I'm solving for A. So if I subtract this 90,000 from this, what is this, 2,250,000? If I subtract this from this, I'm going to end up getting 216, 5, 4 zeros, 3, 4. Whew. And now I want to do the same thing. Have an A squared, I want to get it down to an A. So I take a square root of 216 with 1, 2, 3, 4 zeros, and it should be giving me something around like 14. I'm going to round it to 1469.69, I think is what I'm going to do. Okay, so I know what this number is here now a little bit. This is the 1469.69. So now I'm stepping back. Whew. Find the area of the given land plot in acres. So I kind of went ahead and found this missing dimension. But if I'm looking at this, if I want to know how to find the area of this, I need to know the base and height. So I need to know two things that are at a right degree angle. And if I remember correctly, my area of a triangle is 1/2 base height. And so now I have my base and my height, and I can multiply these two things together, and I can find the area of my triangle. Sorry about that. Let's do this. Okay, so area base of 100 and my height of 1469, 69. And if I crunch these things together, I should be getting something like 220453.5. This was talking about the area. This is in feet squared. Okay. And we haven't really done unit analysis. But if I wanted to cancel out the feet squared, I would put feet squared on the bottom, and I would put acres on the top. And I believe it is 1 acre is equal to 43,560. So I'm going to end up taking this number and dividing it by 43,560 to get to acres. Divided by what? 43,560? Yeah, okay. This is 5.06. Okay. And so there is one sort of last thing that we're going to do in this section, and that is talking about similar triangles. So if we have similar triangles, we can compare these sorts of things. And so I think I went A, B, C line, maybe A line. So there's a few different ways you can number or letter these things, or label them. So I went with A and A prime, B and B prime, C and C prime. So if I'm making these triangles, if I say similar triangles, that means they are the same shape, but not size, right? Not necessarily size. But if they're in the same shape, there should be sort of ratios that we can write between these things. A is B prime, B prime, is one way that we can write this. Another way is people like to go A to B. This is also another way. If we go from here to here, we can also go from here to here. So there are a few ways to write these equivalent ratios between these two things. And so now we get an example to practice this. So I went from primes to doing capitals and lower cases. So we want to find the length of the two missing sides. There are a few, like I said, there are a few ways to do it. So I went from this triangle to this triangle. So if I go from A to 5, that's going to give me one variable. If I go from 13 to C, that's going to give me another variable. I want some comparison that's just going to give me two numbers, right? So if I look here, 10 to 7, it's probably a better one to pick. So if I go from A to 5, going from this one to this one, I want to come up here to 10 and go to 7. So this is one way we can write this. There are a few ways to solve this. So one way, if you have two fractions equal to each other, you just go multiply these things through. So one way is to find a common denominator, 35, multiply both sides by that. And you could get rid of the fractions. It would look very similar to what we're about to write. At some point, they're going to look come back through and come across each other in the way that they get worked, there's going to be a lot of parallels, but there we go. So 5 times 10 is going to give me 50. 7 times 8 is going to give me 7a. So this is telling me 7a is 50. Divided by 7, and I'm going to approximate this. So a is approximately somewhere in 7.142. And the last thing that we're doing here, now we're going here. So from 13 to C, and you could pick this number. I would not pick that number. That is an ugly number to try to compare. I would go back with the 10 and 7. So if we do this, I'm going to skip down here, but we have C times 10. I believe that's going to give me 10C. Now 13 times 7. 13 times 7 should give me 91. And this one divides a little bit more evenly, so C is going to be equal to 9.1, I believe. Okay. There's 2 last little optimization problems that we want to talk about. So the blank has the greatest area of all to do 2-dimensional figures with a fixed perimeter. So if we fix a perimeter, the thing that's going to give us the greatest area is going to be a circle. So if we're talking about a quadrilateral, it would be a square. So if you're thinking a square, I don't think you're too far off there. But the more and more those sides get rounded, the better off we sort of are, right? So regular figures, as we go up sides, up into the infinite-sided circle is one way you can kind of sort of think of a circle. That's going to give us the greatest area of all the 2-dimensional areas. And the blank has the least surface area when compared to other boxes with the same volume. So what has the least surface area compared to volume? That one would be the cube. And there are some justifications we could go behind to why that is, but they would require, I think, something more complicated than what we probably need to get into in this section. And so just kind of knowing that might kind of sort of help you. If you want to make a pin, you're going to make a round pin probably for the cheapest, right? And that would be it for this section. I will see y'all soon.